Hello, good morning, everybody. We will start. I got online a bit later than I usually do, but I think people are joining. Happy Friday. We are finishing off week 10 and we are starting off a new topic. And this topic is going to benefit from what we discussed in our last lecture, which was the stopping point between the classification methods we were considering in the past series of lectures we have had. Today's topic is tree-based methods. And if you remember the last time I sent out a post-class announcement, I said trees and forests will all be covered in this lecture, or kind of, that's what I implied. We will not be able to do all of that. We'll do the tree part and get to forests on Monday. And so this is going to be a method we would learn that would apply to both classification and regression. And it will make use of the discussion we have had on cross-validation on last lecture. I had a lot of fun talking to each one of you on the project meetings. Wednesday was a very, very crazy day, 4 hours of meeting I have had. But I did get to know where you are and get started, and I hope you have benefited. I know there are a couple of you who would have additional meetings, and they may happen this today. And so you're all in good shape and get ready to start. And today also happens to be the submission deadline for assignment 5. And I'll talk about that just in a second. But we are now all on board, and we should do the usual thing first. First things first, we will do a warm-up question. The question, or the discussion today is around trees, and I have the picture that shows what trees look like. And I also know that this is a Friday. So let's have a fun question that is inspired by this, but doesn't necessarily have a whole lot to do with the subject matter. The question is this, and the honor of writing today's question should go to Gordon Duncan. You will be the person to write the warm-up question. The warm-up question is this: what is the most memorable forest or park you have ever visited? Some of you might be into Amazon, I don't know, but what it is your most memorable, something that really was great about that place that you remember. So go ahead and tell me what that forest or park is, where lots of trees are available. So Gordon, you'll write this, and you would also remember to write it one more time for those who may join a little bit later. Tree-based methods is our subject, and we will start. And I'm going to go to our usual place here. Like we have had, I think, a good number of the lectures so far. This one will be based on the book ISLR, and this time we'll go to chapter 8. The last lecture was chapter 5, if I remember right. And so there is a few things that we will pull up from this chapter, and when I have figures and things to discuss, it's good to know where things could be as further reading. So I want to start off by telling you that. And these slides are posted on Blackboard, and you should be able to get them. And the slides, I'll try to make them as complete as possible. But for additional things, you would go there. Since I mentioned it, let me hear, before we really get into the discussion now, where you are. I know a good number of you are doing fairly well in terms of submitting your assignment 5, which is the last assignment you will have. The rest of the time for the semester will be devoted to the project, really, and much of your attention, much of the things that you would have, and the time would go there. And so I want to know where you are now. The deadline is tonight. By midnight. Let me see if there is anybody who would want to tell me where they are. How likely are you to submit on time tonight? And this would be difficult because I am asking people to tell me their favorite forest or park they have ever visited, or memorable one, and I'm at the same time asking another question. So let me give a chance to finish people to write up what they are writing, and let me hear this question that I have for assignment 5 to know where you are. If there is anybody who would want to unmute and speak, that'd be fine with me. But let me see.
I'm 80% done. I just finished the first half of 4A last night, and I'm working on 4B today.
Okay, so let me offer something to the entire class, and I have heard from a couple of you. There were 2 weeks, and I know that one of the, the last one actually is a difficult one, and so Friday is today, and so I don't have a problem extending it to midday tomorrow, if that would help many of you. And that was kind of what I was heading to. And I don't think there will be a disappointment to anybody. So here now, before I hear anybody else, I would say it will be extended to Friday, not to Saturday. And let's call it half day so that you could use the rest of the day for some other things. Whenever there is an extension, it's tempting to kind of use all of that. So let me give you this. And so if you would need to wake up on Friday, Saturday morning, finish up something, so assignment 4B, or for example, you're good. So the deadline is extended. We'll make sure that that is posted on Blackboard. Okay, I'm done with that. Your 575 students, you have a topic to choose for your survey paper. That one is due on Saturday. That's not too bad. Then you can do that and celebrate Halloween after that. So I haven't forgotten that tomorrow is Halloween. Although you're not going to go around, I'm sure, to collect candies. That still is Halloween, and we'll celebrate. You know, you mark it the way you like to do. All right. So deadline for assignment 5 is extended by, let's call it 12 hours. And you have got until tomorrow midday to submit, and good luck with that. And I think it was a good learning experience. And it is heavy or more difficult than other assignments where more involved. So if you needed more time, don't blame yourself. That's what it was supposed to be. Okay. Well, let's get to trees. So we are going to be looking at methods. And one of the things that I want to right away tell you is we're taking this class and it feels like we keep on adding methods, right? So there is this problem we're solving. We had one class of problems called regression. We saw, a linear model for it, and we saw how it could be extended, improved, handle other things and things like that. So we add more and more things to it. And once we came to classification, we in fact started to look at methods, and then we add one after another, after another, after another. And so somebody could ask, why do we have to learn all these methods, right? I mean, why don't you just pick the one that works best? First of all, there isn't such a thing that would say, here is a method that would work the best all the time. And therefore, we just pick it and learn it. The other reason is that some of these methods that work better actually start off by having to do with methods that, like linear regression was, as a starting point for the theory. And then we say, here is what we are adding to that theory, to that method, to that principle, to that workings of it, so that we handle this case, we handle that case, we improve it in this way, we add this abstraction to it, and therefore the methods become important. And so these two reasons are good for having us to look at more and more and more methods. And this cannot be better explained than this with trees and forests. So someone, many in this classroom, would know for whatever it is that the project that they're working on, or whatever it is that you probably would try to apply. If you were to compare trees and forests, you would go with forest. They've got many of them, is basically what it means. But just because they are working better, and ultimately they would give you some advantage over tree-based methods, doesn't mean we should skip the trees, right? So that is why we learn them. And this particular class of methods is applicable to both regression and classification. The technology, the method, is equally good, and we will look at both of them. And so the basic idea behind this is essentially stratifying or segmenting of predictor space. I will round off the discussion today towards the end with pictures that would show you what we're doing with this predictor space. And these predictors, kind of imagine about them and think about them in some space. They live in some space, and usually it's easier for us. We're human beings. We look at the screen, 2 dimensions, and so we usually have, 2 predictors, x1 and x2 or something like that, and that's easy for us to visualize. So if you think of that space, what linear models would do is find a way to get, to the right place by having to work with a line. And now we are going to branch away from that and try to stratify in some other ways. That is what the essence of tree-based methods would be. So I'm telling you what's going to show up in the very last slide when we finish. Spoiler alert. We are going to be using rules to do this segmentation, this predictor space classification or grouping, and that's where the this notion of a tree will come. And so for this reason, this is called decision tree method. These are called decision tree based methods. Let's go for pros and cons first, so that we have justify why we look at them and take excuse for why they fail and what we will do when they fail or when they have disadvantage. So tree-based methods are simple and useful for interpretation. When I listed the list of topics for 575 students for you to consider for your survey papers, I talked about some important topics that are very important now, especially emerging topics in machine learning. And one of them is about having to be fair in our decision-making processes. What are our algorithms doing when they are doing hiring of people, when they are doing other important decisions to be made? Is there bias and things like that? They are there, we know them, and we also know humans are also biased. But what can we do to capture these things are important topics. And one of them, other than bias and fairness and things like that, is how can we explain the algorithm? So if I have a model, if one of these big companies have an AI tool and they're using machine learning and they have something like that, do we have a way to know what they're doing? Can we explain them? Or if somebody has done this for diagnostic purpose or market-related things and so on, it's important. It's not always like the Kaggle challenges may kind of tempt you to think that we've got a model, we've got a machine learning tool, and we are nailing it. We've got the highest accuracy and so on. It's not going to help us very much sometimes if we are at a disadvantage explaining them. So interpretation and explainability is important. What trees have for them, going for them, is that they are simple to interpret. In fact, as we will see now, and some of you already probably know, the tree is the model, and you can show it to somebody, and they would not need to take a class like this or be sophisticated in math to understand it. So that is an appeal. That's a pro. But they are not competitive with some of the best supervised learning approaches in terms of prediction and accuracy, and that is where lots of things would come. Bugging, that's nice. We will have a whole bunch of them. Forest, and you will see why they're called random. And every time I see random, I kind of laugh because there isn't really something that makes you say, oh, I'm going to go to random. That doesn't look like a good thing to do, but it is a good thing. And I have every excuse I got, I have told you why they are. Algorithms benefit from having to do things in a random fashion. And so there is a reason for why that is, but it is a collection of trees, and that is where you would enhance them. Boosting is another one. Basically, what it means is we ensemble. So we get many of them to improve our accuracy and things like that. And so we will look at them. And when we do this, then we lose what we started off with. That means the interpretation will not be that easy. And that could be a disadvantage because now we've gotten what we want in terms of increasing our prediction accuracy, but we have lost in terms of interpretation. And that is a trade-off sometimes. I've already said this, go for decision trees because they can apply for both cases. What we will do for the discussion I will have now is start with regression because it's easier to discuss, and then we'll come back and look at how we change things so that they would apply also to classification problems. We're going to go inside the workings of these things. So let me also tell you one other thing. Just like when we look at different methods, I told you, why do we learn all these methods instead of showing the one that works the best? One, we don't always have one tool that works the best for everything. Second, because these better ones would depend on our understanding of the good ones, so therefore we have to learn them. And then now when we say something like this and we go to study, to learn about how it works, you may also complain about one thing. Am I going to implement it this way? No, we've got tools, and that's one of the things that has become good in our days. Some people in the past have had to struggle to do things on their own, and there was a time when people would do a linear solver themselves. You know what a linear solver is? X equals to B, and so you want to find the solutions for X, and so you have got to do all the Gaussian elimination and all the solver stuff yourself or implement it. You don't do that these days because there are many people who have spent many years of good algorithms, and then we've got tools, software tools, and they would sometimes we don't even know that they exist, but they get pulled out and we work with them. Much like that, we now have tools that would do what I am going to be describing now. And so we should understand this so that first, there are opportunities for us to improve. Second, we would know how they work so that we don't get a black box version of them all the time. That's the basic. Otherwise, what I'm going to be talking about now will be a function call in an R package. And in fact, that's what one of the things I will do on next lecture when we talk about random forest and what you would do. And this ideas first came in the 70s and 80s, and CART, those of you in statistics would know the software package called CART, classification and something. I don't remember the full abbreviation of it. That's a package, and there is another package in R. They are there. And so what we will learn now about the workings of this are already implemented, but I still want you to have an understanding of it. Okay, let's begin to see how they work with an example. And this is an example that is probably something that you all would relate to. It's about baseball players and their salaries. It's color coded. This is a scatter plot. What you have on the vertical axis is hits. And these examples are taken from the book. I have told you which chapter it is. So if you're curious and want immediately read after the class, you can go there, read it. But this is a hits versus how many years they have played. What you have on the horizontal axis is the baseball player, how many years they have played. So the junior ones, just the starters will be, below 5 years, and and some of them have played over 20 years, and these are real, I think. And how many hits they have had is what you see. And color coding of these salaries is like this. So the ones that are low, whatever that number may be, is blue. And then there's greenish, which is also, kind of low, but a little bit higher. And then the higher ones are yellow and red. The red ones are the real high, but the yellow ones are the next to high. So if we were to look at this, and if we were to kind of imagine what kind of linear regression model would fit, we could probably begin to have just an imagination where it would be, but it kind of looks difficult to get a good one. So we could do a good job on this one just by looking at it to try to split this. And if I were to go around and then see around 5 years as a way to say those who are below 5 years, they're really juniors and they're getting low salary, I think I would do a fair job. Just dividing it up that way. Once I start to go after 5 years, it's not that clear anymore. There's a mix of your reddish and yellowish thing, and there's a little bit of greenish thing. There, it looks like there is another indicator I could use, how many hits they have had. And so the more they have had, they get higher salary, which probably makes sense. And the ones they don't. When they're so fresh, they're so juniors, it really didn't matter how many hits they've had. They just equally badly paid. Oh, okay, I shouldn't say that. Low salary, but the higher, when they have experience, they have higher, but it then depends on. And so this kind of stratification could come, and this is what a decision tree basically does. So here's an actual decision tree, and we'll talk about why it's drawn this way in a second. If we 4.5 instead of 5 years is where the split is done. So the first time we did was split the thing into 2 places where we have looked at some of the data that is less than 4.5 years of experience, and the other half is above 4.5. So we go to the left and to the right. Once we went to the right, we saw from the picture that it made sense to see how many hits they have had, and something like 117 hits. When we go below it is 1, and when we go above it is another 1. What you see the numbers there is some kind of score, whatever it is that we have used to estimate, to associate values. But what I want you to see for now from this is that you have split this data, you have stratified it, and gotten a way to get a good way to model it. And the tree was a model. The tree was a model, and we saw where we would place somebody, and whatever it is in the node is what we will give as a value. And remember, now we're working with salaries. So this is, if we were to think of it as a problem for us to predict what salary somebody would get when they are baseball players, we'll give a number, and they will say, they will get 250,000 or something like that. So it's a regression problem, and we had a model, and all our model was divide the wallet into 3 pieces, and depending on year and the number of hits, and we did. From the picture, it looked like we did a fair job. This is what the word version of what I explained. And this is why I told you some of these slides will have something like that, so that when you come back and look at them, you have something complete written. So I'm not going to, spend time retelling you what I just told you. So this is, how we have stratified the data based on the number of years the experience they have had first time and the other classification. So here is what it looks like now. What I told you when you apply the data. Now it's not color coded anymore. So we have got this scatter plot. So the first time we divided it up in along the vertical axis on years, 4.5, and that got a good split. The remainder of it, now we have another region to split, is what the other, the right side of the tree showed, is divided up into two. And we will call these two regions R1, R2, and R3. So R is a notation for region, and this is what we will be using. And there's only one predictor we have used here, or two predictors. One is years, and the other is heats. And we are looking at each one of these regions by saying the condition more mathematically. That's what you see for R1, that's what you see for R2 and R3. And so this itself now has done a good job. And we are going to build up on things where decisions of this sort are done using the help of trees. So let's get some terminologies out of the way for now. So we'll call this R1, R2, R3, the places where we have divided up into the stratification. They will be called terminal nodes. So when we finish the tree will start at the top with the entire data set, and then we will divide up. The place where we stop are called the terminal nodes. They are, this is not a new thing. Computer science students have seen this all the time, starting from their very first computer science course. Trees, unfortunately, unlike the one that I drew at the beginning, where trees are trees and the root is to the ground and the tree grows upwards, we do it the other way around. So we draw them with the leaves on the bottom and the root at the top. That's how it is. The points along the trees where the predictor space is split, they are called internal nodes. So we've got the terminal nodes at the very bottom, and then we have everything else that is used for decision making, like the number of years and heats. That place where splits are made are called internal nodes. So that decision tree had a root, and then internal nodes, and then terminal nodes. This is another wordly description of the baseball data set, where years was the best indicator where things were at the level for salary, that is, when there was less experienced, and when they are more experienced, the number of hits they have had was the one that explained our data the best way possible. So I have already made the case now for this interpretability appeal of decision trees. And this one probably will be a good one. It probably is also sufficient, and you will be surprised to find out for this particular data set, whatever other thing that we would add to make our tree the best way possible will end up telling us that this split into three was actually not a bad thing. We'll actually see that before we go anywhere else. Before we go to having more trees, just with this one tree, we could show at the end that that was not a bad idea at all to divide them into trees. So what is a tree building process? This was the baseball example. It was simple. We could visually tell because of the scatter plots, but we will not always be able to tell what the tree should look like. And that's why the algorithms would come in. This is what the libraries in the software packages would implement. So what we are after is dividing up the predictor space into X1 and X into, these are the P. So we are now having P predictors instead of just two in the salary and on the hits and number of year experience for salary. There were only two predictors, but in general, we can have P of them. And so we're going to imagine dividing up the space that is defined by these P predictors into regions. And we have already seen those R1, R2, and R3, and we will call these regions R1 up to RJ. What is it that makes it decision tree, or in this class of methods? Well, these are non-overlapping regions. So the union of them, when we put them all together, they would give us back the original one. We're not going to leave out anything, but they are non-overlapping. So we had the R1, R2, and R3 in the previous example. The R1 was the east-west division, and R2 was for the right half, the northwest south division. And so we've got these boxes. The union of them will give us the original space, and they are non-overlapping. So that is the question we are going to divide up. And the idea then is for every observation that falls into one of these regions, we make the same prediction. Okay, so we are now dividing up the baseball players into 3 boxes. We say, is your experience less than 4.5 years? Yes. Now you're in box 1. Is your experience more than 5.5 years? The player says yes. How many hits did you have? This answer 1. The player tells us. Now we put them in one box, R2. If they tell us the other way, then we'll put them R3. Everybody is now put in one of these 3. And so whatever it is that we do, the prediction we do for that box will get to that player. There could be 15 players in there, they get the same one. That's the idea here. So we divide up this, and the boxes, the prediction that we get for this one will be assigned to every observation that falls into that box. Now, what does this mean then? What do we need to do to make these boxes good boxes? If we were packing, we would make our boxes so that they would get the most things in them, so that the people, when we get to the airplane, they would tell us, oh, no, your box doesn't fit into the cabin. That would be a bad thing. So we're not doing that. We're not packing. By the way, packing is a real problem, combinatorial problem. What we're doing now is something else. We really don't care about the shapes and other than they are boxes. In fact, we'll actually make that point clearer now on this slide. Other than being boxes, we don't require any other thing on their shape. But what we do care is how well they will tell us about prediction. And that is what this equation that you see is trying to do. So we have each box, Rj, and in each box, we have the mean, the thing that we predicted. Now we are working with a regression problem. The mean that we said is for this box, the one that everybody, every player, every baseball player in that box is getting that prediction, is the average, right? And so we take the difference between the yi and this, and that is the mistake we're making. And we add up this, square it, because we don't care which way we are going in terms of making a mistake. And so that summation now is all the mistake we have made for box J, for box Rj. And we will have J of them. And we want to minimize all of this when we sum them up. That partition is what we're after. And so we have a space to divide up. We have J boxes to create, and the condition we are trying to satisfy to find out how to divide up this thing is to minimize this. And so we have a minimization problem to solve. And this is a partitioning problem. So now let me tell you why we call it box. Theoretically, I could have imagined any other shape. It doesn't really need to have box. But for decision trees and for the math here to work, they are a lot easier to think of them that way. So that means we are working with axes that would be, parallel to this decision making, right? So that we had the cells, and so, left or right, and then we have this other space, up or down. That's how they become boxes. In theory, we could have imagined other ways, other shapes for these regions, and that would have required us a different kind of math, and it will be very difficult to interpret. Okay, so when we do this, when we have a problem of dividing up a space into boxes, some of you might say, oh, I think I know some of problems that are of similar nature. This is a partitioning problem more than anything else. So you can think of this as a partitioning problem where you have an objective function that is given, and so you want to cut into pieces so that a certain thing is achieved. Partitioning problems are very common in parallel processing, for example, those of you are taking a parallel computing class, but the goal there is different. So you want to partition so that there isn't much things to do between the pieces, for example, to avoid communication. Or you want to partition so that load balance achieved. So the boxes are actually of, if possible, as close as possible in size. That's a different objective function. Here we have an objective function that is trying to minimize the error that's made. But still it is a partitioning problem. And so if you have a space and you're going to divide it up into J pieces, boxes, there is what's called exponentially many ways in which you could do that. And try to look for these places and find the one that would optimize is not surprisingly a hard problem, computationally infeasible to consider all of them. When you have that, there's always a way. You always go for something that would be not necessarily give you an optimal solution, but a good one. And these decision tree-based methods are no exceptions. They would be using a greedy approach. In fact, it is also a top-down approach. So we will build the tree not you, but the software that does. And if you write your own, that's what you would do. You are dividing up the predictor space into J boxes, and you have an objective function to minimize. Instead of considering all ways in which you can get these partitions, you would approach this one in a greedy fashion. That means you make a decision one at a time, and you make the decision that seems the best for you at that moment. You don't change, you don't regret and come back and change it. You don't have a way to look ahead and make some other things. You just do one thing at a time, and that's what makes it greedy. In addition to being greedy, this is top down. So you start with at the top, and that decision would be the first thing you would make, and then you would grow your tree down in that fashion. And so this is how the tree building process would work. And I've got lengthier way to say this. We first select the predictor xj for the current point. So for the baseball example, the first thing we did was, how many years of experience do they have? That was where the first selection happened, the one that would do the best job in giving us the clearest picture, the best one so far. And then after that, we would do final refinements. So we select the predictor xj at the cut point s, such that this splitting of the predictor space into the regions less and more would give us to the greatest possible reduction in residual sum of squares. That's the objective we are trying to minimize. Now you would see why it is greedy. Now you would also see why it is top down. You've started with the one that would give you the best one, a very important decision. Then we repeat this process. We repeat the process, but now we have a smaller space to consider. One is left and right divided, and now we take one of these portions and then do the same thing. Again, for splitting that further to minimize the residual sum of squares. And we continue in this way until we come somewhere. What is that somewhere? Well, we could keep on doing this until our boxes are just one item. We were grouping things. So there's no reason we would stop. We could go until we get one in each one of them, but that will be a very bushy tree. And we usually don't do that. And we'll talk about that in a second now. But sometimes you would stop when you don't get a lot of improvement in how much of reduction you're getting in residual sum of squares. So you could say, now it's enough, because the last time I saw, here was what I got in terms of the residual sum of squares or some other measure I have used to measure error, and then say, the last time it was like this, it's just not giving me so much, so I'm going to stop. We've got the stopping criteria. So that's how the tree building process goes. Then once we have built the tree, when we reached out the terminal nodes, we would use the prediction for that box for the terminal node as a way for the entire one that belongs in them. That's how the prediction would happen. So let me give you a pictorial example to show you what is happening when we have two predictors. The first one, this doesn't have details now, so I would probably have a next slide that tells you what these pictures are showing, but let me first tell you. So the thing that you see on the upper left corner is how a partition within decision trees cannot be achieved. So this is something that cannot happen. So we started dividing up things, and then it looks like we're not going into a region and then dividing further up. There is something that goes into this other space, and so they're not boxes. There are certain regions like the one that's hugging on the right is going inside and it's going outside again and things like that. This cannot be a result of a decision tree. This is space defined by these predictors x1 and x2 is not a real one, is what it means. The one you see on next to it is a real one. And so we've got x1 and x2, and it has been divided up in such a way that there is some order to what the partitions are done. So the first thing that has happened is the region is divided into left and right at x1. So when x1 was less than t1, it's to the left. When it is greater than t1, it is to the right. The tree that you see at the bottom here is a reflection of it. So the first partition happened at the root of the tree is x less than t1. When x is less than t1, then you could see now the space is divided up into two, and they are called R1 and R2. This time it's x2 that's used for the decision. And when x2 is greater than less than t2, we call it R1. When it is greater than t2, we called it R2. And that's what you see here. And we stopped and we reached terminal. On the right, we had x we still had the one that is above x2, and then we are dividing it up at t3, and when it is less, we call this r3, and when it is more, we are further dividing it up, but r3 is now a terminal node. R5 and R6 are further divisions of the one that's to the right of this decision at x1 less than t3, and that then the split is done along x2 this time, and so you get R5 and R6. So what you see at the two diagonal positions is the decision tree interpretation of this space and how it is divided, and what you see at the bottom right is how this is as a function seen as a stepwise function to approximate it, basically. So everything that we have done with x1 and x2 now could be seen as linear, piecewise linear approximations to the function that is relating x1 and x2. And we can see that now it has got this shape. That's probably all I wanted to tell you. And as I told you several times now, you will see a picture like this and a little bit of an explanation that you can go back to. Okay, so I told you that when we are working with a tree, we are applying a decision, an algorithm that's top-down and a greedy one, and we could go very far until we get to a terminal node that is just, single observations, and that is usually too expensive. We don't want to do that, and we may even stop earlier when we don't have too much of a progress that we have made. But one thing that would happen when you have a tree that is grown so much down is that it overfits. So if you were to divide up, and then come to a point where you have very few elements in it, you may think like you're doing a good job because you are refining it, but it may end up having the problem of overfitting the data. And so it could do a poor job later on when you are using it to predict. If you stop way too early, and you've got like the baseball players, you divide them whether they're experienced or not, then you would do a poor job in prediction because you have not taken advantage of further things that you could do. And so the truth would usually lie in between. And this is a good example of what you would do when you are thinking about this model complexity and the variance bias trade-off. And this is what would happen here. So if a tree growing like this would make us go to a place where we may overfit if we were to grow it all the way, then stopping too early may make us at a disadvantage because if only we knew that, if we go further, we could have gotten more improvement, but we stopped too early because we didn't ever explore that. Is there a world that would give us the best of these two? Can I find a way to know the future in a way, pick a little bit, but I don't want to do all the things because I would overfit? That is pruning. You do actually have an advantage to grow the tree because you want to make sure that you are getting the best out of it, but you also want to avoid overfitting, and therefore you can come back and then say, I've grown the full tree and I prune it now to get to a place where I have avoided overfitting. That is called pruning, and there is a method for it, and it's so nice. The method that uses this pruning idea has got two ingredients. One of them is very nice for us because we just learned it last lecture, cross-validation. The other is that we have a method that is used now that is actually true of very many other machine learning or statistical learning methods, including when you do linear regression. You could make it fancier, we could do other things, and what you basically do is find a way to add something to your objective function when you try to minimize it. So in our case now, we have this. We've got 10 minutes left, so we should be in good time. Are you following me? Yeah. So what do we have going for us? We have going for us this business of dividing up things into boxes, and the mean of the box is going to be the representative value that we would give to predict, and that would be the one that we are trying to minimize. So the yi minus y, with the hat, the average value for box Rm is what we want to minimize. And we have now a tree with some terminal nodes, and we will show that by absolute value of t. It looks like an absolute value, but it's just the number of nodes you have at the terminal one. So you've got this many, that's how many you have, and so you want to minimize this. This is what your decision tree process would have told you. But you don't want to have too many of these terminal nodes. At the very bottom. So you want to penalize that fact. And so you have the size of the tree added into your objective function that you want to minimize, but then you don't know how much penalty you're going to give this. You don't know where to stop. And so you add a parameter to it. That alpha now is going to be the one that you would look for when to prune. So you've got now an objective function. This is what lasso would mean for linear regression problems. You've added a term to your objective function. That was the original one. That you are now adding a penalty term to it, the price you pay if you were to go all the way down. And so by having this now worked out in a good way, you prune your tree and you solve your overfitting problem. And the method for doing this is going to, the way we find alpha is going to be something called the weakest link pruning, or the cost complexity pruning, which is what finding alpha would mean. So we are going to be doing this by having to work out for alpha by using cross validation, because now we can split our training data into test and training and use cross validation. The same grill we learned last time. That was to find out how well our method was doing. But in other words, we are also looking for a way to how well our method is doing. So the cross validation now will make us assess or find out a way where to get our alpha in a good way. And so this is the pruning algorithm described in full detail. The idea there basically is what is a good value for alpha, and you would find that guidance by running a k-fold cross-validation on your data set to determine a good choice for alpha. Because you've got an objective function that have incorporated alpha itself, now you have not too much of a difficulty. I know you don't have enough time to digest all the 4 points written here, but I have kind of given you the intuition to find a way to know where there is a mistake and to get to a place where it gives you the minimal value. So there will be many trials, many attempts. That's why you have a repeat steps 1 and 2 here. When you do this repeatedly and come to a place where you gave you the best value, that will be your prune tree. Fortunately for you, when we get to see code and you call a function in R or in Python, this sort of things are hidden. And so you probably wouldn't know this is going, but it is at least one of the times when you see the inside of it and how it is working. So for the baseball example that we saw before, we could do this and see what our alpha would be. Now that we know, we have got this data set and it has got some number of players and it is divided halfway. 132 of it is used for training and the other half is used for the test set, because we are going to use cross-validation to determine our alpha to prune our tree. And so we have this data set that we already know, and our task now is to find a good value for alpha. In other words, where to prune. And here is the full tree. This is the full tree when we grow it, and we stopped it in our initial example into three pieces, R1, R2, and R3. If we were to grow it fully, and our stopping criteria is we will stop when each of these boxes has got 5 players in it, no more than 5 players in it, not exactly 5, but no more than 5. This will be the full grown tree. So we'll have something like, I think it's about 10 or 12 of them, children. And don't worry too much about the numbers that are showing at the bottom. It just means whatever it is that you are saying, some value that has been computed. And this tree is actually a result of what you would get when you use R. It's a depiction, and it looks a funny tree because some of the branches are tall, some of them are short. Whenever you see tall, it means the division at that terminal with that decision variable has done a good job splitting things or dividing things up. And when it's not so much, it is shorter. That's what this basically means. And so now we could do this cross-validation thing, our pruning thing, for this data set. And what you see on the horizontal axis is the size of the tree. That's how many terminal nodes you have. And what you see on the vertical axis is the mean square error, because this is a regression problem. And you pay attention to 2 curves first. One is the black curve, that's the training error, and the other one is the red curve, that is the test error. The training error and the test error are known quantities to us. So we've divided our data into 2. There was half of it which was used for training, the other half for testing. And so the more trees we grow, we don't get surprised that the error goes down. This is exactly what the bias trade-off curve we saw last time told us. So the more complex the model is, that's what the tree size would mean. Now your error goes down, 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 down. The test one doesn't necessarily do that. It starts to go up when you start to overfit. And remember, what you have on the horizontal axis is how many children you have or how many terminal nodes you have. What you see with the green curve is what you did with this cross validation where you determined alpha. And that value and what you did with the test kind of agree. At least their pattern is very similar. And it looks like the minimizer for this, the one that gave us the least error, looks like is when the tree size is about 3. That's why I told you we were doing a good job with these baseball players, just dividing them up into 3 boxes. Our prune tree confirmed that. Okay, we don't have a whole lot of time. Everything I told you now would carry on when the problem is a classification problem. That is the point of the remaining few slides. So you will not blame me too much if I go a little faster now. So when it was prediction, we minimized error. We will do the same thing when it is a classification, except that now we will have a different way to measure error. The other thing we would do is when it was a prediction problem, we said we will have a value that would be an average for each box, and that will be what everybody in that box will get as a value, the average. Now, because it's classification, we don't do average because we've got classes. What we do assign is in each box, the one that is the most commonly occurring class would be the one that everybody would get. So the majority would vote here, and that's what you would get. These are the 2 distinctions from how you would use a decision tree when it is regression versus when it is used for classification. So let's start with what error measure you would use. Residual sum of squares and mean square error, those were the ones for regression. When it is classification, you would use something around misclassification rate, how many mistakes you have made. And this value that you see here, it kind of talks about that. So where this P with M and K, this is the the class that it has been assigned to. The place where you have done the maximum mistake is what this one would count. And so you have a function that really kind of gets into the place where you are talking about misclassification rate in a maximized version. This would have been ideally the thing that you would use to mimic what the residual sum of squares or the mean sum of errors would have done for a regression problem. This is not a good choice because it kind of messes up with the decision tree making process. It's not smooth. And for that reason, people have come up with better ones. And one of the better ones is called a Genie Index. I'm not sure if it's pronounced Genie or Genie. Some people say Genies, others say Genie. This one has got this expression. And if you are still following me, which I hope you are, you may see whatever it is given in that summation looks like a binomial. And it is a binomial. And so you would convince yourself that this is trying to measure a binomial just, function in a way. And it is a way of measuring purity. So this value would be small when, it's, the classes that you have are kind of pure. Whatever it is that you have saying now would tell me all that are in that same class. When it is the other way around, it would be getting a maximum value. So it's a measure of purity. Genie Index, a very useful one that helps us in making decision trees build in a smooth way. There is another one that is related, but is also equally attractive, and it's called cross entropy. Both of these things are actually things that you would encounter when we get to deep learning. Cross entropy is a common function, objective function that you could include to do classification in a manner that you are measuring how well it is doing. So we've got our measures taken care of. The rest is similar, as I told you. And all I will do in the minute I have now is give you one example, just like the baseball players, another one that is about classification. And this time it is about heart data or disease. And so there's patients that have complained about some chest pain, and they are going to be categorized into one of 2 groups. They've got heart disease, they have no heart disease. And there are 13 predictors for doing this: age, sex, cholesterol level, and a number of other things. And we're going to see how decision tree does on this. And this is a real one. And this is an eye test also for you to see if you can read what I have written on this screen. Don't blame your eyes too much. You can go in the book and look at it. But what you see on the top is a decision tree on those 13 predictors when they are used to classify things. And what you see on the bottom is what our pruned tree would do. There is training, there is cross-validation in the test. And what you see on the right is a tree that's pruned by the guidance of this cross-validation method. And it does do a good job with only 6 terminal nodes compared to however many the top one would do. So it is doing a good job on this one with decision trees. my time is 10. This was the last slide I wanted to tell you that why we learn different methods. And here is a picture when linear models are doing a good job and when decision trees would do a better job. If you are in the world that looks like the upper portion where there is green and yellow division, and this is what you were to predict, then go for linear, because that line that you see there would do the job the right way. If your world was not like that, but it is more of this, the lower half, where the truth is this type of regions, then whatever you do to your linear model, however sophisticated you would get, it will never do a good job. Whereas a decision tree-based method would just nail it. It will get it exactly right. So this is why we learn different methods, because there are things where one would do better than others. I've got a last slide that talks about advantage and disadvantage. The advantage, we have talked about them all along. And the disadvantage is that decision trees would do a poorer job compared to other supervised learning methods. One way to get them better is to have many of them. And that's what we will do when we look at forest on Monday. And this is where I want to stop. All right, I did go a little over. I'm sorry, I didn't have time to ask questions, but does anybody has a quick question for me? You're all eager to go.
There's a question about the survey paper in the chat.
What is the question? Can you?
For the survey paper proposal, we just need to propose the topic and not the paper. Is that correct?
The paper is what you write. The survey paper is what you would write. All I read now is a topic. So don't misunderstand. The survey paper is what you would write. That's what you will submit in December 7th, right? So the topic is what I am asking for now. And I will do is, this is a good topic, go for it. Or I would say, change your mind and pick this other one or something like that. So it's just the topic now. That's why it's an easy one. But you should think about it, right? Choose something that you're interested in and something that would be meaningful. And that's why I would also look at whether it would make sense or not. Yeah, so it's just the topic. It will be 3-4 lines when you submit now. You will tell me the topic and you will tell me why. If you want to tell me in more than 2 sentences why you're picking it, you're welcome. But I think most people would just be fine telling me in 2-3 sentences.
Thank you.
Sure. All right, I apologize being a couple minutes late, but I think it was needed. So we'll pick up on this one and also to look at some codes for doing decision trees and random forest on Monday. All right, have a good weekend, and you've got a 12-hour extension for your assignment 5 submission.